Hello everyone, let's pick up where we left off last time. We looked at pre-K participation and its impact on year-end score. So we essentially asked whether a child went to pre-K or not predicted the year-end score. We noted that this was a categorical variable, and therefore we transformed it into, in this case, a dummy-coded predictor. A dummy-coded predictor is just coded as 0 and 1. So last time we indicated that if a child did not attend pre-K, we coded that as 0. If they did attend pre-K, we coded it as 1. And when we did that, we looked at whether or not there was a significant difference in year-end score based on whether or not a child had attended pre-K. And we did that through the regression analysis. So we went up here and we did analyze regression. Linear. Final grade is the dependent variable, and pre-K recoded into a dummy variable. We ran the analysis. We saw that, yes, attendance at pre-K is a significant predictor of final grade after year 1. P-value of less than 0.05 and R-square of 0.177. And we discussed what the coefficients represented. The beta 0, as is before, the y-intercept, or the group coded as 0. And this was going to be the actual difference between the two groups. So beta 1 using dummy codes was the actual difference between the two groups. All right, so let's pick up there and now move on and talk about what the text describes as contrast-coded predictors. And let's create one. So as you can see, this syntax here creates a new variable called pre-K3. It assigns a -1 to all the values. But it tells SPSS to go back and take another look at pre-K, and if pre-K equals y, meaning yes, recode it into 1. So let's go ahead and run that. All right, so now we've created our new variable, and as we said last time, SPSS does not always run the transformation for you. You may have to come here and run pending transformations. There we have it. And we have a new variable. We could go ahead and do that quality check that we talked about last time with crosstabs, but let's go ahead and run the analysis. All right, let's swap out and add our new pre-K3 variable and run it. Okay, what we're going to see is the exact same F value and the exact same R-square value. We're also going to see the exact same T value. So if we take a look back, we can see that the T of 3.531 is the same T value we had before. We can also see the ANOVA table is the same, 12.471. Right. However, what does change are the coefficients. We have to think about this a little bit. The coefficients here were determined by the variable pre-K3 coded as -1 and 1. So let's go back to our graphs, because the graphs helped us understand this. We used a scatter plot, and we used a basic scatter plot. What we did was we put final grade on the y-axis, and we put pre-K recoded as a dummy variable. Now this is the analysis we did previously, and let's take a look at what happened. All right. What we saw was when we moved from 0 to 1, y increased by the exact amount of the coefficient. It increased by 7.567. And that made sense. As we moved from one group to the other, that was the actual difference between these two groups. And that's because we were coded 0 and 1. It made the interpretation nice and easy because we increased by 1 unit. Remember that interpretation of the coefficient is if x increases by 1 unit, y does this. Well, in this case, y increased by approximately 7. So the line went right through here like that. Well, let's see what happens in the case of a contrast-coded predictor of -1 and 1. Well, you see that it's elongated a bit horizontally. And that's because we've stretched out the range, or the value of pre-K 3. We haven't coded it as 0 and 1, we've coded it as -1 to 1. So when we're interpreting the coefficient now, it doesn't make much sense to go from -1 to 0, i.e. a 1 unit increase, because we don't have a group coded as 0. So we are actually going 2 units. So when you increase x by 2 units, you would have that same 7, difference of approximately 7, the coefficient you saw before. So then it makes some intuitive sense that really this coefficient should be half of that. And so this 3.783 is actually 1/2 the difference between the two groups, because we have stretched it out from -1 to 1. If I recoded the variable into -5 and +5, we would expect our coefficient to be 1/10 the difference between the two group means, because there are 10 units going from -5 all the way up to 5. That leaves the y-intercept. The y-intercept here is still the value of y at x equals to 0. So it's at this point here in the middle. And therefore, it makes intuitive sense again that this is the grand mean. The grand mean means it is just the mean of y, is the mean of final grade after year 1. So 75.517 is just that overall mean of the dependent variable. All the test statistics are the same, but by changing our coding, we change our coefficients. So 3.783, to summarize, is 1/2 the difference between the two groups. All right. Let's forget about pre-K right now, which is a dichotomous predictor, and talk about a categorical predictor with 3 levels. Now, one could make an argument that this is ordinal data, not categorical data, in that you could argue that high school progresses to college, then to graduate, so that there is some type of trend there, but it's probably not linear. And in fact, we're not going to call it ordinal, we're just going to call it categorical for the purposes of this exercise. And so what we need to do now is create a set of variables to test parental education and whether or not parental education is a significant predictor of year-end score. And we don't care about the other variables now. We're not considering pre-K anymore. We're just looking at parental education. All right. Well, the first thing we notice is this is no longer dichotomous. It's not going to be easy to just set up one variable that tests what we're interested in. So in your readings, both in the text and the notes, that you have come across now and realized that when we have a categorical predictor, we need one less number of variables to account for the various categories, or that predictor. So in the case of pre-K, we had 2, and therefore we only needed the 1. We did it 2 different ways, but we saw that they were essentially equivalent. Here we have 3 levels: high school, college, and graduate. Therefore, we're going to need 2 predictors in order to account for parental education. So we'll go to our syntax, and we're going to have to create 2 different variables. Okay? So we can forget about pre-K for now. Don't let that confuse you. We're going to create 2 different predictors, and I'll call them PE1 and PE2 for parental education. So what does that look like? Well, let's use these variables. Let's compare parental education of high school versus the other 2 together. And then let's compare college and graduate level of parental education. So PE1 here will compare high school to these 2 together. PE2 will compare college to graduate. All right, so we need that syntax here. The syntax becomes a little bit more complicated in that I need to create 2 different variables, PE1 and PE2. All right, so PE1 is going to be somewhat straightforward because we're going to have -1 for both of these groups and just a 2 for the other group. So what I'm going to do is start out with -1 and just create a variable that's -1 for PE1. And then I'm going to go back and tell SPSS, hold on, if parental education is high school, change that to a 2. For the second PE2, I need to code as 0, 1, -1, and 1. Again, these negative signs we can switch. All it does is change the direction of the coefficient. Likewise, if I put a -2 here and 1's here, I would just change the sign in front of the beta. That's all. Still the same test. So for PE2, I'm going to need an extra line essentially, because I have 3 different values here. I have 0, -1, and 1 that I want to have. So I'm going to go ahead and start out with -1 again. You can choose 1 or the 0. But I'm going to change graduate to +1. I'm going to change high school to 0 to align with these codes. I want high school equal to 0. I want graduate equal to 1. Right. Now, you notice I put execute here this time. You'll see what that does in a moment. Alright, so it looks like we don't have an error message. That's always great. And you can see here, I don't have to go run pending transformations because I put the execute sign there. Essentially, it told SPSS to go ahead and run that transformation right now when I added execute. All right, let's go ahead now and run the regression. So I'm going to use parental education 1 and parental education 2. Put them in. I think I'll paste this syntax. And I'm going to go ahead and add my ZPP and my tolerance. Tolerance is going to be interesting. Okay. All right, we see there's a significant difference. So let's start out with the ANOVA table. We see that we have an F of 3.438, a p-value of less than 0.05. What does this tell us? Well, this tells us that, yes, parental education is a significant predictor of final grade after year 1. What it doesn't tell us is it doesn't tell us where the differences between the groups lie. The ANOVA table just tells us overall that, yes, there's a significant difference in there between groups. Yes, it is a significant predictor of final grade after year 1. But the ANOVA table doesn't tell us where, because now we have more than one predictor. So in the previous examples, we only had one predictor, therefore t-squared from coefficients table is equal to the F in the ANOVA table. That's not the case here, as we have 2 predictors. So we know it's a significant predictor. We don't know which groups differ. In order to get the accurate ANOVA table, you need 2 predictors because we have 3 levels of the variable. Model summary tells us that about 10.8% of the variance in final grade is explained by differences in parental education. So not a lot, right? There's some other important predictors we're missing. So let's come down to the coefficients table. We'll come to the significance test and the coefficients themselves in a moment. But what we're going to look at first is this tolerance. Notice that it's 1. And that's because we created variables that were orthogonal. So see the text and the notes on this. These are a set of orthogonal contrasts. And in fact, these are Helmer codes. I believe the text might reverse the negative sign here, but that, again, that's fine. All that does is change the sign of the coefficient. Okay? So if you want to check whether or not these are orthogonal, first you need to add the column and see that it equals 0. This does as well, equals 0. Then you need to compare each set of codes. So each pair of codes. Here we only have 2, so it's quite easy. We simply multiply 2 times 0, add that to -1 times -1, add that to -1 times 1, and you get 0, plus 1, minus 1, 0. They're orthogonal. Just a quick mention here, if we have a categorical variable with 4 levels and there's 3 variables, you need to compare each pair in order to show the orthogonality, not multiply across all of them. All right, so what we can see from these codes are PE2 is pretty straightforward. We got rid of high school by assigning that a weight of 0. However, here we assigned -1 and 1. Well, we know this from our contrast code that we just talked about, that PE2, the coefficient is going to be 1/2 the difference, because I'm going 2 units, between the mean of college and graduate. level of education, parental education. How many units do we move from -1 to 2? Well, we move 3. We move to 0, 1, 2, so 3 units. So the coefficient of PE1 is going to be 1/3 the difference between the means of parental education for high school and college and graduate combined together. Right? So if you actually just calculate those means, you'll see that what these coefficients represent. So PE1 is 1/3 the difference between high school and the other two combined. And it looks like there's a significant difference. So having one of those higher degrees does significantly predict final grade after year 1 when compared to a high school degree. The sign is negative, so we need to consider that. So what happens with our codes? Well, as we go from college and graduate up to the 2 value of high school, the average goes down. So what does that tell us? That tells us that the average here of college and graduate is higher than the average score on after year 1 for parental education level of high school. That's important. That tells us which mean is higher. And of course, we're interested in that in the practical sense. We're not just interested in seeing there's a significant difference. We're interested to see if one is significantly larger. And it tells us here, the sign of the coefficient tells us that as we moved from college and graduate together to high school degree, it went down. Therefore, the college and graduate level mean is higher than the high school level mean of final grade after year 1. Okay, the next coefficient is, of course, comparing college and graduate level education and its effect on final grade after year 1, and we see that there is no significant difference. So we can't say this is different from 0 significantly. If you want to know what this represents, 2.075 represents 1/2 the difference between college and graduate levels on the variable of final grade after year 1. So this is 1/2 the difference. So if you just looked at the two means for parental education, you would see that half the difference between the college and graduate level on final year after grade 1 is 2 times this number. Again, with the contrast-coded predictor 75.517, we know is the grand mean. It's the mean of final grade after year 1. And so the tolerance will be equal to 1 here when we use these orthogonal contrast codes. When we use something like dummy codes, they will not be. Okay? But we could set up a set of dummy codes for this exact same variable. We could look at parental education through a dummy coded predictor. What would that look like? Well, what that would look like is we would need to first decide, is there a particular group I want to compare to? So let's just do that quickly. All right, so I'm going to show you a set of dummy codes. All right, so for dummy codes, you have to choose a reference group or a comparison group. So you do that by assigning zeros in both cases for a categorical variable that has 3 levels and therefore 2 variables. So let's call this dummy 1 and dummy 2. Okay, so you have to pick a reference group. And so what is going to happen? D1 is going to compare graduate to high school. And D2 is going to compare college to high school. So whatever is set as zeros across represent the reference group that the other groups are going to be compared to. Okay, so in this case, D1 will compare graduate to high school, and D2 will compare college to high school. And so you would then go ahead and create those variables, which are pretty simple to create because you're just dealing with 2 different levels, 0 and 1. So they're very easy to create in the syntax. Then run the analysis. And what you'll find are a few differences. You'll find that the tolerance is no longer equal to 1. Okay? So one of the major advantages of orthogonal contrasts is that they're completely uncorrelated. A tolerance of 1 means that these two variables, if you correlated them, the correlation would be exactly 0. So interpretation is quite nice. They're uncorrelated, there's no overlap. However, remember from the beginning of the last screencast, your research questions are going to determine the types of codes you use. If they are orthogonal contrasts that are provided in the notes in the text, or they are dummy codes, we know exactly what is being compared. And that's great. If your research questions go away from that, it gets a lot more complicated. We'll address that before the end of the course, but for now, this is a good place to stop.